And so if we look at this structure here, this molecule is called benzene. We have central atoms. Each of these carbons are central atoms because they're bridging more than one atom. But these hydrogens are all terminal, because that's where it ends. Chain ends there. Molecular geometry versus electron pair geometry. That's okay. Molecular geometry is the geometry of the atoms. Electron pair geometry is the geometry of the groups, electron groups. Angular is another word for bent. And so this is bent versus trigonal planar. Different. Trigonal planar versus trigonal pyramidal is different. Trigonal pyramidal versus tetrahedral. If you draw them, you can see it's different. A polar molecule is going to have bond dipoles when you sum them up over 3 dimensions. They don't equal 0. It's a non-zero. Versus a non-polar molecule, bond dipoles sum up to 0. Bond dipoles either are 0 or they sum up to 0. Was it 72?
Yeah.
Okay, 72 is C6H6. Well, when we draw C6H6, to get everything to have an octet, we're going to have multiple bonds. And it's going to be a ring structure like this, hexagonal ring structure. And so this is what we call benzene here. When we look at the EPG of benzene, the EPG is what? How many groups of electrons are around? Well, when we're talking about the EPG, we talk about the EPG around each central atom. And so let's pick one of these, like this carbon. How many groups of electrons around carbon? 3. Single bond, and a double bond. There's 3 groups. And therefore it's trigonal planar. And then we look at the Mg. The bonded atoms are the same geometry, which would be trigonal planar. And if we look at all these carbons, all the carbons are the same. These are all trigonal planar carbons, which means that this is like a pancake. It's flat, basically. And so this is the benzene ring. And so benzene is a planar compound in which the carbon atoms are arranged in a hexagon. A Lewis diagram for this molecule has a geometry that accounts for the observed shape of the molecule, including bond angles. Draw this diagram. And so this would be it. The bond angles would be all, what? Sure. What is the bond angle for trigonal planar? 120. So all the bond angles are 120, no matter which 3 you pick.
So I was a little bit confused on how you got double bonds for this structure.
How we got the double? If you okay, basically, if we follow the there are 2 ways of building for organic compounds. For organic compounds, we could either sum up the electrons and come up with some kind of backbone and then fill it in. But what I do for organic is I have something like this, and so we're trying to put these together. And so if I try to put these together, well, I can go to, let's say, carbon to a carbon. That. And then a carbon to a hydrogen. And then maybe another carbon to a carbon. Yeah. So I could do something like that, but it's kind of hard. And so what we sometimes do is we do this. I look at all the bonding environments that the carbon can have. So it's got 4 valence electrons. With 4 valence electrons, it can have 4 single bonds. An alternative is it could have 1 double bond and 2 single bonds. Or it could have 1 triple bond and 2 single bonds. Or 1 single bond. 1 single bond, 1 triple bond. So in this case, organic chemists have a little rule. If it's all single bonds, then what you do with the hydrogen is you double it, the carbon. And so you double it and then add 2. And so I can tell if this were all single bonds because it would be C6H12 plus 2 would be H14. And then I know that, hey, that's all single bonds. And then, so right away I can tell there's gotta be multiple bonds here because I don't have enough hydrogens in order to bond everything. And so, those are little clues that we get in deriving the structure. The other clue that they're giving is, they're telling us it's a ring of 6 carbon atoms. And so let's go ahead and do a ring of 6 carbon atoms first, all single bonds like this. Okay, then I have 6 hydrogens. Well, let's put 6 hydrogens here on each carbon. If we put 6 hydrogens on each carbon, then I'm still short. You know, I need one more bond to the carbon, but I don't have another hydrogen to bond to the carbon. So in this case, I got to think of something else. And the other thing I got to think of is multiple bonds. And so the multiple bonds, well, I have 2 choices. I could do multiple bond like this. If I put another multiple bond here, I have a huge problem. What is that problem?
Carbon can't bond with anything.
Yeah, this is 5 bonds. Carbon can't have an expanded octet. It's not going to form 5 bonds. So I'm going to alternate the double bonds. And so this is one structure I can come up with. But why did I pick this one to make the double bond? I could have picked this one to make the double bond. And so I have 2 choices for making double bonds. I have this one here, and then I have this one here, which makes a double bond in the alternate sequence. These are called, what are these 2 structures called? Resonance forms. And these are the only 2 choices I have for benzene. So this is it's kind of a cheater. When you get to organic, then you know it's going to be like this, it's going to be like this, and it's going to be like this. And then once you know how many hydrogens there are to fill things in, then you can figure out how many bonds you need. So for example, here, if I do C2H, if I do C2H6, then I know it's all single bonds. Because here it's okay, carbons are bonding together, and then I have 3 hydrogens on each. That's C2H6. However, if I have C2H4, then I already know I have a double bond in there, you know, because otherwise I'm not going to be able to complete everything. So there's going to be a double bond here. And so in organic chemistry, they already have seen this, so they can just go right ahead with C2H4. If I have C2H2, then, oh, for sure I have a triple bond. Got a triple bond there because I have it. Otherwise, I'm not going to have enough bonds. I need 4 bonds to each carbon. And so this is how I'm going to get it. And so I skip, you know, organic chemists, they skip all that, you know, sum up the electrons. They usually skip all that and just go straight to drawing it. Now, they say this. They say they're trying to cover their bases here. They're trying to cover their bases because they don't want you to get the wrong impression. And so this is the impression that they're going to leave you with. Experimental evidence shows that the diagram does not describe the structure of benzene accurately. So if it doesn't, you know, if it doesn't describe the structure of benzene accurately, then isn't that kind of like Bohr? You know, does Bohr describe the electron accurately? No. So should we say, okay, learn Bohr, and then at the end have a little footnote? The little footnote says, well, this picture of orbits doesn't really describe the electron accurately, and then leave it at that? And so there are 2 things here. One, it doesn't describe it accurately because it turns out that neither resonance form is accurate. What's accurate is this. What can happen is the electrons, the bonding electrons, can rearrange themselves here. So for example, if I push these electrons over to this bond, and these electrons to this bond, and this electrons, I get this structure. And if I do that again, I'll revert back to that structure. And so what this is called is delocalization. In other words, I don't localize the double bond here because the double bond can be placed over here. And in fact, the whole thing is what we say delocalized. In other words, it would work if there's a wall here. If there's a wall here preventing electrons from moving here, then we call it localized. And sometimes there is a wall here. You know, sometimes we can't not move the electrons there. And but this is like the bathtub. You know, if you have 2 feet of water, 1 feet of water, 2 feet of water, 1 foot of water, 2 feet of water, 1 foot of water, that's fine as long as there's a barrier, so that we can put 2 feet here, 1 foot there. But if you lift that barrier up, then what's going to happen to all the water? All the water is just going to spread out over the entire ring. And so what is more accurate is what we call the resonance hybrid. And so the resonance hybrid is going to be the average of the two structures there. And so rather than having single, double, it's going to have 1.5 bond to each. And so there is a single bond fixed, but the double bonding electrons are going to be smeared out over the entire structure. And so one way to show that it's smeared out over the entire structure is just kind of dot it in there like this. And so that's showing the double bonding electrons can be smeared out, or delocalized, we would say is delocalized over the entire ring. And so the what would be a more accurate picture of this or structure of benzene would be the hybrid structure. The hybrid structure is more accurate. And so it's that. So here are the two resonance forms. For benzene, these are traditionally called Kekulé structures, but they're just resonance structures here. Typically, the hybrid is shown in two ways. I'll show you how we show the hybrid structure. Hybrid structure is delocalizing the double bonding electrons over the entire ring like this. So it's either shown as dotted line like I did here, or it can be shown as a solid ring like this. Sometimes to save time, you don't draw the carbons in there, just show the carbon-carbon bonds. So here's the ring. These are each carbon-carbon bond, and then the delocalized double bonding electrons here. And so this is the typical, when somebody sees this, they go, oh, that's benzene. So. And so, yes, the resonance hybrid is going to be more accurate. Different structures, different drawing, different ways of drawing this. These these structures are based on something called valence bond theory. Lewis structures in general are based on valence bond theory. And valence bond theory is quantum mechanics based. Is valence bond theory the full version of quantum mechanics? Do you know what to describe benzene most accurately, this is more accurate, but still this is not the most accurate. You know what the most accurate structure for benzene would be? Well, the hybrid comes from Lewis, it comes from valence bond. Obviously, this resonance form is not the most accurate. What's better is to show all the resonance forms. What's better than that is to show the hybrid. And what's better than that is to not use valence bond theory, but to use the full quantum mechanical treatment of the benzene molecule, which is called, anybody remember? Well, let me see if I can trigger some kind of memory. What was it? Chapter 12. Yes. It was during this slide I talked about it. Anybody remember? We can draw the Lewis structure of oxygen. And I go, okay, well that's fine. Well, I look at this is linear. All two atom structures are linear. If I look at each oxygen should be EPG. 3, which would be trigonal planar. The Mg is going to be linear, however, because it's just two atoms. And so that's the Lewis structure there. Is it possible to delocalize? Can I come up with any resonance forms for this? No. No resonance forms for this. So that looks good. I don't have this problem with the hybrid. The hybrid's better than the resonance form. Turns out all the bonds in benzene are exactly identical. And all the bond lengths are the same. This would be a funny distorted hexagon because double bonds are shorter, single bonds are longer. So it would be distorted, but it turns out it's a perfect hexagon. And so this one, there's no resonance forms here, so this must be it. This must be accurate, correct? It turns out no, it's not, because they throw this at you. They say it is impossible to write a single Lewis diagram that it satisfactorily explains all the properties of molecular oxygen. And so what does that mean? That means the Lewis structures are not giving us, or not predicting the correct properties. Kind of reminds me of like the Bohr theory. And so what did we do with the Bohr? Bohr theory was unable to make predictions, therefore pretty much disregarded the Bohr theory. We didn't even bother studying it in detail because it was wrong. And so what are we doing? We're drawing these Lewis structures, and these Lewis structures aren't accurate portrayals. And so maybe we should drop these Lewis structures and use some other approach. And that is exactly what we can do. We can drop this and use another approach. Except the problem with the other approach is the other approach is quite difficult. And so it turns out when we look at this, the Lewis structures like this are based on something that we call valence bond theory, which deals with these atomic orbital overlaps like this. So when we look at the orbitals that are involved, so like these are p orbitals here. These are a different kind of orbitals here, called hybrid orbitals. But the best approach is to use molecular orbital theory. Molecular orbital theory is full quantum mechanical treatment of benzene. And so we start getting these kind of images for electron clouds, you know, this kind of stuff. But it's quite a bit more involved. Whereas it's very easy to draw the Lewis structures. Drawing all these molecular orbitals and mapping out the electron density is a lot harder. You can't just do this with pencil and paper. Lewis structures and hybrids and resonance form we could do with pencil and paper. Was any math involved here? No, there's no math. This is a lot of math is involved here. You know, so we aren't doing that. And so this is why this has not been like disregarded like Bohr, you know. It's still pretty useful because it gives us a pretty close idea of what's happening, but it's not the most advanced. The most advanced would be molecular orbital theory, or MO theory. This is the quantum mechanics light version, which we call valence bond theory. This is what we're doing. In Chem 1A, you do this type of stuff. This is the more advanced type of stuff. It's called molecular orbital theory, which you also do in Chem 1A. All right. So that's number 72. Any questions? Any other questions? Benzene is an important molecule. It's also a component in gasoline. You might, be at the gas